from IST. Professor Chandrasekhar is requesting you to give some brief remarks, opening remarks at this. Please go ahead. Yeah.
All right. Thank you, Dr. Krishnamurthy. It is so nice to be part of this program. Actually, it is an excellently designed program, and you have top experts in the country who have contributed tremendously, both in upper atmosphere and lower atmosphere. They are there as speakers. So I congratulate Chandrasekhar to get all these speakers to make presentations in this program. I would like to say a few words about the real challenges that face the atmospheric science. Over the last 2 to 3 decades, we made a tremendous program, both in ground-based as well as satellite-based experiments. Satellite-based experiments primarily in planetary sciences, and ground-based experiments, we have this major facility which started as an MST radar facility. This is a very high power radar, which I will be talking about, and Dr. Patra and Dr. T.N. Rao will also be talking about. How we came to establish this high power radar facility. There is a small history to it. Way back, at least from 60s, 70s on, from PRL, some senior scientists, from NPL, from several universities, they have been asking for a very high power radar. This is what is called an incoherent scatter radar. Only 2 or 3 facilities are there in the world at that time. That is the Arecibo Observatory in Puerto Rico, started by Cornell University, and another one in Jicamarca that was also set up by United States, that is in Peru, right on the equator in South America. So they realized you will not be able to make much progress in predicting the lower atmospheric process, climate and the weather, without having some idea about the dynamics in the middle atmosphere. Because many of the circulations do not extend down into stratosphere and mesosphere. So stratosphere and mesosphere do have some influence on the lower atmosphere, although not to the great extent, but they do have. So one has to view the atmosphere as an integrated system from ground to about 100 kilometers. So that was the view back in the days of 70s and early 80s. And Dr. Sidney Bowhill, Dr. A.P. Mitra, and a few other top scientists, internationally well-known scientists in atmospheric and space sciences, thought there should be an international middle atmosphere program. So the middle atmosphere program started, and in India, we started actually what's called Indian Middle Atmospheric Program. And Dr. Dhawan was the chairman at that time of Department of Space, and Professor Daniel was the chairman of the Advisory Committee for Space Sciences. And so the scientists presented to the Department of Space about the need of a high power radar to investigate the middle atmosphere and upper atmosphere. And that idea was taken, was considered very favorably when Dr. Daniel put it up to the chairman, DOS. So the DOS chairman has um, contacted all the DST secretary, UGC chairman, and others to join as a national, as a multi-agency facility, a high-power radar facility. So this is a unique facility supported by 6 or 7 departments of the central government. DOS is a nodal agency, DST, UGC, Department of Defense, Department of Electronics, and the CSIR all joined in establishing this facility at a cost no more than 10 crores at that time. And no one visualized what has been achieved in these 20-25 years. You will be listening to the talks this morning from Dr. Patra and Dr. T.N. Rao. They will be giving great details, but I will be giving some introductory kind of a talk, provide you a background leading to how the ground-based, particularly the high-power radar, contributed greatly not only to the middle atmosphere, to the lower atmosphere, and what critical science questions have been taken up so that they could advance our ability to predict weather and climate. So with these few words, I would like to thank Professor Chandrasekhar and Dr. Dadwal for giving me this opportunity to share some of my views on particularly the radar probing of the atmosphere and ionosphere. Thank you. And any time you just give a signal for me to start my talk. Thank you.
Thank you, sir, for sharing your valuable and long experience. It gave us a complete background about the history of atmospheric remote sensing in India. You also gave very valuable insights on the facilities that are now excelling in this field. Thank you, sir. I now invite Dr. A. Jayaram to deliver his opening remarks on this program.
I hope, yeah.
Yeah. Yes, sir, you're audible. Yeah.
Okay, good morning to all of you. At the outset, I should congratulate IASP for conducting this faculty development program on an important topic. Particularly, I thank Professor Chandrasekhar, Dr. Dadwal and colleagues for inviting me. Of course, I will be talking on Saturday about LiDAR, but this is just a few introduction, since I have been asked to say a few words. As actually Dr. Dadwal also said it, Director IAST said it, the talking to faculty is nice in the sense that I always used to say each faculty in turn going to teach, say 100 students. So if 50 faculties are attending, actually we are 50 into 100, right? So and at the same time, we are also cautious that those we are giving the talk, that we are going to teach, we are teaching the teachers. So we have to be careful, and I'm really glad that this topic is taken, and there are experts like Professor PB Rao, who is the pioneer in the MST radar and has been nurturing the MST radar facility, and a host of other experts are there. So I am assured of the participants that yes, you are going to have a good time. Please be watchful, and I am sure Professor Chandrasekhar will appreciate you to ask questions also, but maybe if you think it is difficult to ask in between or interrupt, there is always a chat box. So I see it nice as and when you get a doubt, you can start putting it in the chat. It's my view, okay? The convener may say, but this is what I feel. I say, so you can put your questions. So at the end, if the time and the speakers can keep some time, so they can address one by one and the question. And of course, this pandemic, otherwise we could have been there in Trivandrum enjoying the hospitality of Dadwal et al. But we are now in our respective cages thanks to COVID. But nevertheless, as somebody said, here there is no back bench or front bench. You know, when we are talking on our terminal, everybody is in the front bench and you are too close. And you cannot complain that I cannot see the slide properly because slide is on your screen very much. So please enjoy and have a good time. Thank you.
Thank you, sir, for your well wishes and for your encouragement formula of 50 cross 100 impact factor of this faculty development program. I now invite Dr. A.K. Patra to deliver the opening remarks on this web program. Patra sir, kindly unmute. We are looking forward to hear from you. So in the meanwhile, till Patra sir joins us, I invite Dr. Ramarao from Indian Institute of Space Science and Technology to kindly give his opening remarks about this session.
Thank you, JT. Good morning, all. Respected Director Dr. V.K. Dadwal, Registrar Dr. Vaidyanak Krishnamurthy, Dean Academics and Coordinator of this program, Professor Chandrasekhar, and Dean Research, Dr. Raju Jaj, Dean Student Welfare and Affairs, Professor Kurvila Joseph, my colleagues and students and other distinguished speakers of this FDP. It's heartening to see this luminary of several areas at one place, and it's great opportunity for the participants to be here and to listen to the technical and directional aspects of great research arena, which is a combination of both remote sensing atmosphere, including all the aspects of ground, air, and satellite. And I thank you once again for the speakers to be here for us to enlighten us. And the participants, this particular program is second of this year in IAST to be organized by Department of Earth and Space Sciences. On behalf of Department of Earth and Space IAST, I warmly welcome you all for this 5-day program. Just a brief of this department is that we have got 3 distinct disciplines of Earth and Space Sciences. One is remote sensing, other is Earth System Science, and the third one astronomy and astrophysics. This particular program is a combination of disciplines of remote sensing and Earth System Science, particularly the atmospheric sciences, wherein the remote sensing tools and techniques, and the principles of atmosphere and the applications have been fused in such a way that it's an intensive program which can be useful for students, researchers, and even well-established researchers to pursue further works and get updated in this thing. And the programs is such that there have been a lot of sessions also which are partially hands-on. And I congratulate and thank the coordinator of this program, Professor Chandrasekhar, for making this amalgamation of so many things in one event. Despite a very short time it was. And thank you very much. And we extend a warm welcome to all of you once again. And we hope that this program will be very fruitful to all the participants. Thank you again. Thank you all.
Thank you, sir, for your brief introduction about the program to the participants and your wishes to the participants. I now invite Dr. A.K. Patra, Director, NERL, to kindly deliver the opening address on this session. Patra, sir, kindly unmute. Welcome, sir.
Yeah. Very good morning to everybody. Let me first thank Director of IIST, Professor Dadwal, and Professor Chandrasekhar, and Dr. Krishnamurthy sir, and for considering me to be a resource person for this particular activity, where you have taken off the faculty development program sponsored by ICTE, and I'm extremely happy to be part of this particular program. And Professor Rao, PB Rao, who is known to be a giant in the radar probing of atmosphere, ionosphere in this country, he is also part of this program. I'm extremely happy to be part of this. And I actually congratulate IIST for organizing this kind of program, which not only brings the faculties from ISRO, but from other, department of ISRO, DOS, and also I am not sure about this, but maybe other faculties from university and colleges. I do not have the full list. I'm sure this particular program in remote sensing of the atmosphere, ionosphere, and space weather, I think will benefit the participants, and we will all try to provide as much information that we can give to the user and make this particular program very, very successful. Thank you for giving me this opportunity.
Thank you, sir, for your opening remarks to this faculty development program. We all are looking forward for many more sessions, the hands-on and the expertise session in upcoming days. Now we have a few minutes of break and we will rejoin at 11:30. I request all the participants to kindly rejoin on time, and we will continue with the session after 11:30. So thank you all for being there in the welcome session.
Yes. Jayati, just one small remark. Dear participants, as you could have seen the requirement of attendance from ASTE, in the past there are so many cases where some of the participants unfortunately could not able to get their certificate because of this attendance shortage, and we don't want that kind of scenario. In the sense, we don't want anybody to be disappointing. So I kindly request you to attend the sessions and answer. We will be finding attendance in such a way that we'll be giving a question which can answer instantaneously. So kindly do that so that we will have the ability and opportunity to support you in all the documentation required for you to get the certificate from ASTE. So kindly do this, for all these sessions of this 5 day. Thank you all, and we'll meet. Professor Chandrasekhar, so participants maybe shall we have a short break? So, unmute, sir. Unmute.
So the first inaugural talk of this FDP program on atmospheric remote sensing will be given by Professor PB Rao at 11:30 a.m. Okay.
We look forward to see all the participants there at 11:30. Thanks for the session.
So my talk will be at 11:30, madam?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Good morning to all the participants. In a short while, we'll start with the first lecture of this session.
Good morning to all. We are moving on to the first lecture of the day. Our first talk is on radar remote sensing of atmosphere and ionosphere by Dr. PB Rao, NRSC. Dr. PB Rao received his PhD in ionospheric physics from Andhra University. He worked as research associate in Electroscience Laboratory, Ohio State University, and National Center for Ionosphere and Astronomy, Cornell University. He was director of the NARL during 1990 to 1998. He continues with the Department of Space as honorary visiting professor at the NRSC since 2002. He has published more than 130 papers in space and atmospheric sciences. He also received several awards, including Raytheon Distinguished Author Award, Asian Ocean and Geosciences Distinguished Lecturer Award, and he is an elected fellow of Indian Academy of Sciences. He also served on several national committees, includes the INSA National Committees of COSPAR and URSI, Department of Space Committee like Advisory Committee for Space Sciences, Scientific Advisory Committee of the Space Physics Laboratory, VSSC, and NARL. So with this brief introduction, I welcome you, sir, for the lecture. Over to you, sir. Hello, sir.
Just just a few seconds. Sir is putting into this login. Connectivity is there.
I already spoke to him. Joining in a minute.
Bibin Rao sir is here. Can you just introduce him once again to the audience
Okay.
and welcome him for the session? Thank you.
So we are moving on to the first lecture of the day. Our first talk is on radar remote sensing of atmosphere and ionosphere by Dr. PB Rao, NRSC. Dr. PB Rao received his PhD in ionospheric physics from Andhra University. He worked as research associate in electroscience laboratory, Ohio State University.
Hello?
Yes, sir, I'll take care.
Yeah.
Good morning to one and all. I welcome you again on the first session. So we have a talk on radar remote sensing of atmosphere and ionosphere by Dr. PB Rao from NRSC. Sir has received his PhD in ionospheric physics from Andhra University and has worked as research associate in Electroscience Laboratory, Ohio State University and National Center for Ionosphere and Astronomy, Cornell University. He was the director of National Atmospheric Research Laboratory during 1990 to 1998. He continues with his Department of Space as honorary visiting faculty at NRSC since 2002. He has published more than 130 papers in space and atmospheric sciences. He has also received several awards, including Raytheon Distinguished Author Award, Asian Ocean and Geoscience Distinguished Lecturer Award, and he has been elected as Fellow of Indian Academy of Science. He has also served on several national committees, including the INSA National Committee of COSPER and URSI Department of Space Committee, like Advisory Committee for Space Science, Scientific Advisory Committee of Space Physics Laboratory, BSSC, and National Atmospheric Research Laboratory. I welcome you, sir, on this occasion, and we invite you to kindly deliver your expertise talk on this session. Rao, sir?
Yeah, can you hear me?
Yes, sir. Yes, sir.
Welcome, sir.
Okay, let me put on my slides. All right. All right. Can everyone see the slides?
Yes, yes.
Yes, sir.
So I will
Kindly
start my
make
talk.
the full view, sir.
Pardon me?
Make the full view. Just press.
Screen. Yeah.
Yes, sir. Right side bottom that cup.
The
Yes, sir.
slides
Yes,
are.
yes, yes.
Yeah, now it's fine, sir.
Thank you,
It's
sir.
okay. All right. First, I would like to thank Dr. Dadwal and Professor Chandrasekhar for giving me this opportunity to give this talk in this faculty development program. It's indeed a great pleasure to be giving this talk. Now, the title of the talk is Radar Remote Sensing of Atmosphere and Ionosphere. Radar is an active remote sensing instrument, and I will give first the history of the radar, how it is came to be invented, and its evolution over the last so many decades. I will start since the beginning of the radar. It's an interesting story. That is the elementary part of it, and will form the background for understanding the more recent developments, not so recent. Since 60s, we have come to use the high power radars for atmospheric and ionospheric studies, particularly the structure and the dynamics of the middle atmosphere and upper atmosphere. Then under that, how the high power radar works, how the signal scattering mechanisms for the high power radar operation. And the MST radar is basically mesosphere, stratosphere, troposphere. That's the middle atmospheric region, and that is explored using the MST technique, radar technique, high power radar technique. And in fact, that is the only technique that can be used to study the middle atmosphere, because satellites cannot reach, satellites or rockets cannot explore that effectively, that region. And the third is the signal and radar signal and the data processing techniques, how you extract the signal from the data or the products, atmospheric products like winds and turbulence parameters and the plasma irregularities from the signal return. Finally, I will give some sample radar observations. To start with, what is the radar? Radar is radio detection and ranging. It is you send out the radio waves, a pulse of radio waves, it detects a target and it finds its range. So radar is an acronym for radio detection and ranging. And that is how the ionosphere, a conducting region in the upper atmosphere, came to be discovered. So what was the motivation or the scientific events that spurred the development of the radar, that led to the development of the first radar? There are two scientific events. One is the invention of radio by Marconi in 1901. Another one is totally unrelated to the first one, radio science, and that is the observation of the fluctuation in the horizontal component of the Earth's magnetic field, delta H, over the equator, detected over the equator. So these are two unrelated events. How these came to influenced the development of the radar is both these scientific events suggest there must be a conducting layer somewhere up in the atmosphere. The first one is the long distance communication of the radio signal is possible only when there is a reflector in the atmosphere. A reflector means a conducting region. So it suggests there is a conducting layer up in the atmosphere which reflects the radio waves to explain the long distance communication of the signal, radio signal, which Marconi has done. That is the invention of the radio. And the second is delta H, that is the fluctuation in magnetic field. And any change in the magnetic field calls for some current flow. And this one is a daily phenomenon, a diurnal variation. Every day, the magnetic field goes up by about 60, 70 nanotesla. The rise starts in the morning, peaks up around the noon time, and comes down to the base level by nighttime. So the basic level is 0.3 Gauss or something. It goes up by a small fraction, delta H, during the daytime, and it peaks up around the noontime. So it's a transient daily variation, and it got to be from a current flowing in the atmosphere, because it cannot be accounted by the current flowing within the core of the Earth. So these two events, that is the invention of the radio and the discovery of a fluctuating magnetic field, horizontal component of the magnetic field, daily variation of the horizontal component of the magnetic field, both these suggest that there is a conducting layer up in the atmosphere. First, to reflect the radio waves, and the other one, they allow the currents to flow to account for the variation of the magnetic field. So it is in search of this conducting layer, the radar was, an instrument was developed which is called the radar. That is, you send out the radio pulse and it detects a target and find its range. That is, detecting the target in this case is a conducting layer, and find its range means its height. So this is Guglielmo Marconi, who won the Nobel Prize in 1901 for inventing the radio. On December 12, 1901, he could succeed in sending a radio signal across the Atlantic from east coast of England to St. John's in Canada. That's transatlantic distance of 2,100 miles or 3,300 kilometers. Incidentally, no one believed that radio waves can propagate beyond the horizon because electromagnetic waves, radio waves, are nothing but one part of the electromagnetic spectrum. Electromagnetic waves do travel in straight lines, and they cannot be bent around the curvature of the Earth. And so people thought the radio waves can propagate only up to the horizon. That is the radio horizon. I mean, now we call it, which is slightly beyond the optical horizon. All the diffraction and everything gives a little bit beyond the optical horizon, which is called the radio horizon. So all the theoreticians, physicists believe that the wireless signals, they call it the radio telegraphic signals, can be sent without the wires up to the horizon, that is about 50 to 100 kilometers or so, and not beyond beyond that. Marconi doesn't have a formal education, and he would not understand all that diffraction theory, and so he started experimenting with this wireless telegraphic signals, that is the coded, Morse coded signals in short distances first, a few hundred meters, and then a few kilometers and beyond. Eventually, he thought he can send the signals beyond long distance around the curvature of the Earth, very long distances, and that was the first experiment, which was not supported in Italy, his native country, but his mother is from Ireland. There is some connection to England. So the British Postmaster General is willing to support his experiment. That's how the first experiment was conducted. So this is how the radio works. As you can see, when you transmit from an antenna, the electromagnetic waves, they go in straight lines. And if there is no reflector above in the atmosphere, the rest goes straight. And beyond this horizon, this is all the shadow region. If there is an antenna here, you will not be able to see. But then the distance from England, the east coast to England to St. John's, Newfoundland, Canada, is a transatlantic 3,000, beyond 3,000 kilometers. So it is inevitable. People thought there must be a reflector to reflect the radio waves. So this is the sketch for showing the reflector kind of thing. And the next one shows this is the magnetic field, the horizontal magnetic field. This is the perturbation part taken out, and it goes and peaks up in the noontime and comes back. So it's a daily phenomenon, and this also tells that there must be currents flowing in the atmosphere. So this was first noted by Johannes Carl Friedrich Gauss, and it was many observations were made by Arthur Soster has established that. So those two initial experiments set the stage to for the discovery of the invention of the radar. So people thought, what kind of an instrument is needed to detect that conducting layer? So two engineers, US engineers working in University of Wisconsin, Breit and Tilley, Gregory Breit and Tony Tilley were the engineers who built a pulse radar. They know in order to detect and find out the range, require a pulse, an electromagnetic pulse to travel, and it interacts, it gets reflected or scattered from the target and comes back to the receiver. So you find out the time delay for the radio pulse to travel and come back. From that, you can find out the range. So they have built a pulse radar, which is this is a block diagram of the similar to the one used by the first inventors of the pulse radar, that's Breit and Tilley. The first stage, actually you will feed a rectangular pulse and a CW radio signal, that is the RF signal, and so at the bottom you can see the radio signal, and this is an RF signal pulse, and RF signal, and then so it will keep on repeating. So this is the pulse repetition rate, and this is the pulse width. So those are the two crucial parameters. So that is the kind of pulse that comes to the transmitter, which is actually a series of amplifiers, an voltage amplifier in the front stage and successive power amplifiers. So that will generate the high power signal, radio pulses here. And this duplexer is a switching mechanism. When the transmitter is on, it will connect to the transmitter. Then after the transmitter pulse is over, it will switch to the receiver, to the front end of the receiver. So the signal is transmitted into the space, and the receiver signal through this switch is connected to the front end of the receiver, that is an RF amplifier. And then it goes to the mixer with the low loss level. It's a heterodyne receiver to a low frequency thing or a medium frequency from 400 kilohertz or something. And the radio frequency could be in megahertz, usually the HF range, few megahertz. So the first experiments were conducted between 2 and 20 megahertz signal was sent. Actually, it is in the MF range, 500 kilohertz to 3 megahertz. That is the frequency range of the RF signal. So that signal is beaten down to a few hundred kilohertz. It's an IF amplifier, and then peak detector, and then the low frequency signal. That is the video signal. That's the radio signal, peak detected, will be displayed. So there will be a signal coming from the target after it's a very, very slowly varying signal that can be displayed. So its position with respect to the transmitted signal actually will tell if the signal comes around here from the delay, you know, what's the speed of the light. From that delay, you can find out the range of the target. So that is how they detected a reflecting layer, a signal at about 100 kilometers above the ground. And this is the layer that was predicted by one American engineer and one American scientist and one British scientist, Kennelly and Heaviside. Heaviside is a British scientist, and Kennelly is a US scientist. They both predicted soon after Marconi's experiment that the conducting layer must be there up in the atmosphere around 100 kilometers. And this is the first evidence by Brett and Tuve that there is a reflecting layer in the atmosphere, and that's called the ionosphere. So two English scientists used a CW experiment, that is the continuous wave experiment. Instead of pulse, they have used a continuous wave. And if this is Edward Appleton, who won the Nobel Prize for his studies on ionosphere in 1947, and his associate Miles Bonnet, and both worked in UK, and they conducted different kind of an experiment. This is the CW experiment, and this is called a bistatic radar. Monostatic means the transmitter and the receiver are at the same site, and a bistatic radar means transmitter and receiver are separated by some distance. there are two ways to find out. Of course, the signal gets reflected from the conductor back to the ground. This is a long distance propagation. So you know the base distance between your transmitter and receiver. So you have to find out the vertical distance. That can be done by two ways. One is if you know the angle of arrival of the signal. So let me see. All right. Sorry about that. So this is Appleton-Barnett experiment. So there are two ways to find out the range of the ionized layer reflecting this radio waves. One is to find out the angle of arrival. Then it's actually the angle of incidence being angle of reflection. Then you will know this angle. And then the distance, half the distance, and then you can find out the the slant distance, and then of course the vertical height. That's one way. The second way is actually to detect actually the ground wave and this sky wave. There is an interfere the receiver, and there is an interference pattern. So this, if h dash is the total path of the sky wave and h is the path of the ground wave, that divided by the lambda, the operating wavelength of the radio wave, that give the number of interference fringes. So what they have done is an ingenious way is if there are n number of fringes for a lambda, for an operating wavelength lambda, they change the operating wavelength slightly to change the number of fringes by 1. So that is n plus 1, that is n dashed. So by changing the operating wavelength slightly from lambda to lambda dashed. So you know the distance, horizontal distance, that is, the distance, that is the separation between the sky wave path and the ground path. And then you know lambda and lambda prime. And so you can find out the D, which means h dash minus h, and you know h, that is the horizontal path. So you can find out the slant, the total distance h dash, this path. Now half of that will be the slant distance, and from that you can calculate the height of the layer. So those were actually the early experiments that led to the invention of the ionosphere. The conducting region is called the ionosphere. So this is Robert Watson-Watt, who actually coined the word radar. That's the radio wave detection and ranging. And he's the one who built the first pulse radar in 1935 to detect an aircraft. That is a bit difficult. You can find out the range. I did not tell about how the radar has evolved. A pulse radar, if you use wide beams, then you can find out the range but you will not be able to locate where exactly it is located. So from the transmitter and the receiver, if it's a monostatic radar, the range can be anywhere over the half circle around. So because you do not know the angle of arrival. So to know exactly where it comes from, you should know the angle of arrival of the thing. That is the next stage. If you know the angle of arrival and the range, then you can locate the target. So what is the next stage? If the target is stationary, you can find out exactly its location. But if it is actually moving, the reflected signal will be Doppler shifted. So you will have to find out that Doppler shift to find out the velocity with which it is moving along the direction of sight from the receiver. That's what is called the Doppler velocity. So along the line of sight of the radar to the target, you will find at what velocity the target is moving. So an aircraft is a moving target, so it is called a moving target indicator. That's what Robert Watson-Watt called his instrument. That is a radar, which is now referred to as a Doppler radar. So a Doppler radar can find out the range, its location, and where exactly it's located, and also its velocity, so where it is moving. So that is what he developed during World War 35. He demonstrated the first radar. By 39, he perfected the radar and placed so many radars as a chain. It's called a chain home radar network all along the coast of England to detect the enemy radars. That was the World War II. To detect the Nazi bombers, aircraft bombers, he has used this chain of radars. First 5 radars and later expanded to 19 radars covering the east coast and the southern part of the England. So they could successfully locate the incoming aircraft from Germany to locate and then shoot them down. So that has decisively changed the course of the Second World War, the people believe. So the radar invented by Robert Watson-Watt, it is the pulse radar. The invention was for the scientific reason, as I mentioned to you, by Brake and Tuve and Appleton and Bonnet already demonstrated, and that led to the development of the radar for defense application by Watson-Watt. So this is that moving target indicator, MTI radar. So the only difference is it's a pulse radar with the capability for angle of arrival. What he did was put a huge tower and vertically stacked the cross dipole antennas to find out the angle of arrival. And then he actually fed the same signal which actually generated the transmitted signal. The same signal is fed to the phase detector. After coming back the IF amplifier, here it will be mixed with the transmitted signal, and it will detect not only the amplitude but also the phase of the received signal. So the phase and amplitude, if you receive, then it is possible to find out the speed of the target, moving target, because the time rate of change is equal to the velocity, the Doppler velocity. That is the velocity along which the radar beam looks the target. So from that you can find out. If you find out these velocities from 3 different radars, non-coplanar radars, then you can find out exactly in which direction the aircraft is moving. Otherwise, you will know only the line of sight velocity. So that was the network of radars that Robert Watson Watt has fielded in UK could find out the aircraft, enemy aircraft location, its movement in all the three components of the velocity vector, exactly in what direction it is moving. So that is what the first Doppler radar was developed during the World War II. So these are some of the important radar parameters and the target parameters. How the radar parameters are related to the target parameters. So the first is the interpulse period. So you will be sending the pulses intermittently. So the time delay between the pulses is capital T, and the pulse width is the duration of the pulse, which is related to the bandwidth of the pulse, which is 1/tau is the tau is seconds is the pulse width, and 1/tau is the bandwidth, and the power of the peak power of the RF signal is PT, and the average power means the duty cycle is pulse width divided by the interpulse period multiplied by 100 is the duty ratio in percentage. So that gives the duty ratio multiplied by the peak power gives the average power of the transmitter. So the range to the target is you measure the time delay T from the ground pulse, because the ground pulse means right located at the transmitter, you immediately receive the transmitted pulse, which is 0 time thing. From that, with respect to that ground pulse, you measure the reflected pulse from the target, the time duration T. So that CT/2, the 2 comes because it is a two-way path. The radio wave goes up to the target and comes back. So the range is 2R. 2R is equal to CT, so the R is equal to CT/2. So the unambiguous range is the T/2, that is the interpulse period. So if the target is located more than CT/2, so the second pulse will be coming and it will fall beyond the second pulse. So there is an ambiguity in the range. So the target should be within the duration, that is the interpulse period. That is the first pulse to the second pulse to the third pulse and so on. So, so there will be a sequence of pulses that you will be sending, and the target will be occurring after each pulse at a given range, and on oscilloscope you will see at a fixed range. But if it goes beyond the interpulse time T, then there is an ambiguity, because it will come after the second pulse after another small time. So you will not be knowing, and that is what appears on the oscilloscope or in your receiver. So if it is a 1 millisecond interpulse period, if it occurs at 1.1 millisecond, so it will appear as if it is coming 0.1 millisecond after the transmitted pulse. So it is not 1 millisecond. So that ambiguity will be there. So the unambiguous range is of the target, which means the range, the maximum range you can detect, is determined by the interpulse period. So you should have an idea of up to what height your targets are located. If there are multiple targets, you should know the target that is located at far off place. So that is, excuse me, that is the significance of that unambiguous range. And the range resolution is you are sending not a very narrow pulse, it is a finite duration pulse. So it illuminates the target simultaneously over a range delta R. So if the two targets are placed less than delta R, then you will not be separating, you will not be identifying as a separate targets. So in order to detect multiple targets, if there are two airplanes which are closer than the delta R, then of course you will not be able to look at each one separately. So in any case, any two targets in sky observed by a monostatic radar, it can resolve the separation of the radars if it is more than delta R. Tau is the pulse length. And the signal power, received signal power is PS, and PS minimum means so as the signal propagates, it gets spread because of the antenna as a broad beam. So the power density keeps on decreasing, and the power captured by the target is power density divided by what is called the scattering cross section. So that and then it scatters back, and then the received signal again spreads, and then the signal will be coming down in its strength as the target is farther and farther away, and eventually there is a background noise, cosmic noise, as well as your receiver noise, which is called noise power. If it is less than the noise power, you will find it difficult to detect the target. So that is PS minimum. So these are actually scattering cross section, actually the signal power for a single target. This is the transmitted power and gain of the antenna, and A is the receiving antenna aperture, and the target scattering cross section is sigma, and the range to the target is R. So R to the power 4. So the signal power, received power, keeps on decreasing as your target is farther and farther away. So it decreases at the rate of R to the power 4. And if there are multiple targets, then SN will be, you will have to actually integrate the scattering cross section of each target. So the total received power will be within your pulse volume, that is the radar pulse volume. If there are n targets, so you will integrate all the scattering cross section of each target, and that is the summation, and that is the n targets integrated each one. Sigma I is the ith target radar cross section, but the radar equation is essentially the same thing. This is for the n targets, and that is for the discrete targets, that is solid objects. And if your target is a distributed target or beam field, sorry about that, and this is for a target which is beam field means if it is an atmospheric target, soft target, atmospheric turbulence, then whatever is the beam width, and then the beam vertical dimension, that is actually this one, it will keep on increasing as the radar beam propagates up into the atmosphere. it keeps on filling the whole volume. So that is a distributed target. So the target includes all the reflectors, all the scattering targets. In this case, in the atmospheric case, it is the turbulent scatterers within that volume. They will be scattering. So in that case, the scattering cross section, the signal power is so you will have to integrate. You will have to find out the volume of the atmosphere that you are actually that your pulse occupies, and that is this is r theta. Theta is the angular width of your antenna, transmitting and receiving antenna. And then we talk of the sigma, which is actually scattering cross section of the entire all of the volume illuminated by the radar beam. Since it is filling the entire volume, it is equal to eta into delta V. Eta is what is called scattering cross section per unit volume. So that is a very important parameter in atmospheric and ionospheric probability. So we will be talking about scattering cross section per unit volume. So the total cross section divided by the volume occupied by the pulse is called the eta. It is called the scattering cross section per unit volume, and that is actually the atmospheric scattering cross section. So this is going back into the HF communication. As you keep on increasing the frequency of the radar signal, the conducting layer cannot keep on, the signal keeps on penetrating deeper and deeper, and as it is proportional to the electron number density. The frequency, as you increase on, it will go and gets reflected at a level what is known as when its frequency is equal to the plasma frequency, and the plasma frequency is related to the electron number density. So it's electron number density square is proportional to the plasma frequency omega 0, that is the angular plasma frequency, where the plasma frequency is equal to the angular frequency of the radar signal. That is where the signal gets reflected. So if the conducting layer has a maximum electron number density, then there will be a corresponding maximum density plasma frequency. Plasma frequency is nothing but the oscillation of if the electrons are displaced slightly in the conducting region, and they will have a natural oscillation like Brent-Poisson frequency, and it is a natural oscillation of the plasma, and that's what is called plasma frequency, and that's related to the electron number density. So your radar frequency equal to the when you are actually transmitting vertically up, the radar frequency equal to the plasma frequency. That is where the group velocity comes to 0, and the signal gets reflected totally and comes back. And if the ionized region has a peak density, and that's up to that point, the vertical radio wave gets reflected. And then if the density decreases above that point, then it penetrates that region, and you will not be able to get any reflection. That's what happens in the case of the ionosphere. So as you are increasing the frequency, for oblique frequency, this is the critical frequency, that is the vertical frequency escaping frequency, or the critical frequency at which the operating frequency penetrates the ionosphere. So that is the maximum frequency. So the maximum usable frequency for broadcasting a signal from transmitter to the receiver is vertical critical frequency divided by secant theta. Normally, the vertical critical frequency is about 10 to 15 megahertz, and it is multiplied by secant theta. That's theta is the zenith angle greater than 1, or divided by cos theta. Then it can actually support the signals as high as 20-30 megacycles. So that is actually the original radio. So the broadcast signals going from in the HF range from 3 megacycles to 30 megacycles were used extensively in the initial days of radio for communicating the radio signals over long distances, global. That is global broadcasting radio signals. So that is how the radio works. So people are now interested to know, since there is a direct application for broadcasting communications, people are interested to know how to actually find out what is the maximum usable frequencies that could be used. That is how the vertical probing of the ionosphere. So if you know the vertical electron density profile, then you can find out the maximum usable frequency for any range from your transmitter, for 1,000 kilometers to 2,000 kilometers or whatever. So that is how there is an instrument that is developed to find out the electron number density, which is related to the max critical frequency, the vertical critical frequency of the radio wave. This instrument is a sweep frequency radar, HF radar, which will sweep from 0.5 megahertz to 15 30 megahertz, and then at certain point it keeps on varying, increasing in height, and it penetrates the ionosphere. So the frequencies usually there are two radio waves. Since there is a magnetic field, the incident wave is split into ordinary and extraordinary waves, and those we are interested in the penetrating frequency of the. These are very close, separated by only the zero frequency. So we find out the penetrating frequency, and from that we can find out the maximum usable frequency. That is what is now called an ionosonde, and this is the one which will map the electron number density from lowest height to the peak of the electron number density. So then the electron number density falls down from this peak. This is the total electron number density, and the upper part is not visible, because any radio wave that penetrates the peak, it can escape into the air. So that is how the ionosphere has been investigated using the HF radio waves. So this is the evolution of the radars. First invention of the radars in the HF range, MF to HF range, that is the 300 kilohertz to 30 megahertz range, and the detection of the targets, the aircraft, by Robert Watson Watt. Then came the weather radars. These are microwave radars spanning from L band to W band, that is 1 gigahertz to about 90 gigahertz, which include weather radars and the cloud radars. And Across and Richter in the United States in the 40s are the pioneers in developing the weather radars. Then came the what is called the incoherent and coherent backscatter radars. First they came for the ionospheric studies, and these were built in the first radar in Hikmarka. Of course, the first an incoherent scatter, I have to tell, this is the scatter from 3 electrons in the ionosphere. The reflection comes from the refractive index gradients or the reflection stratification of the conducting layer. But then, in principle, you can get a backscatter signal from each electron. So the free electrons can scatter back the signal. So a very weak signal does come back, but that is very difficult to detect. That's what is called an incoherent scatter signal. That comes from the entire height range of the ionosphere. So you can map not only the ionospheric electron number density, but also the electron and ion temperatures and their motions and all that using the high power incoherent backscatter. That's how the high power radars were introduced to investigate the ionosphere first. Later on, it came to be recognized in '74. The Hickamarca radar has been used to measure the winds in the middle atmosphere, below 100 kilometers. They thought there is a refractive index fluctuations in the atmosphere, and the power of the radars is such that they should be able to scatter the signal back to the receiver, and that's how the high power radars came to be used to explore the middle atmosphere. That is the mesosphere, stratosphere, troposphere. And so Ron Woodman in Hickamarca, he was the one who has first detected the MST radar signal. And then MST radar signal become very popular because it's only technique that could investigate with very high temporal and spatial resolutions the atmospheric structure. That's the from ground to 100 kilometers atmospheric structure dynamics. In essence, the winds, waves, and turbulent structures can be mapped by this high power radar. So now we move to the high power radars. I would like to know at this stage how much time I can take in this one. There are two more talks that follow my talk.
Yes, sir. Sir, you can take half an hour more.
Yeah.
Okay. All right.
Your lecture is going very interesting, so I hope like all the audience are also enjoying it. It's very informative.
So I actually spent quite a bit of time on the history.
So next session starts from 2 o'clock. So from 1 to 2 we have a lunch break. So till 1:15.
What time I stop? At 1 o'clock?
Yes, sir. 1 and a little bit more you can take.
1 o'clock?
Yes.
Yes.
Okay, I had to go quickly then. This gives you actually the refractiveness. Fundamentally, the high power radars work on the principle of radio wave. You send out the radio wave into the atmosphere and it gets scattered back. Actually, it doesn't get, you don't get a total reflection. It gets scattered back from refractive index fluctuations. And the refractive index fluctuations are basically two different types. One is random fluctuations. You can get, that's from turbulence, you can get. Another is a stratified kind of layers. Like if there is a strong change, I mean, very rapid change in temperature or humidity layers, then the refractive index changes abruptly, then you can get a partial reflection. That's what is called Fresnel reflection. And the backscattering is actually a turbulent backscatter. I will tell you why it is called backscattering. And the third is a different kind of a thing. This is Rayleigh scattering. Rayleigh scattering that is from individual particles, and that's used to detect hydrometeors, or that is the raindrops. So these three scattering mechanisms, the first two, or to study the clear air turbulence. The turbulence acts as a tracers of the background wind. So you can find out the wind by tracking the turbulence in the atmosphere, and also turbulent fluctuations themselves you can find out. So the turbulence parameters and the winds can be measured by the clear air turbulence. And the Fresnel reflection, that's the structure. Actually, inversion layers, temperature inversion layers, or trapped humidity layers give you a partial reflection. Those can be identified and located using the Fresnel reflection. And the third is Rayleigh scattering. This, whenever there is rain, the raindrops, each drop scatters back. It's a Rayleigh backscatter. A small, the particle size is less than the wavelength of your radar. Then it's called the Rayleigh backscatter. And you get the Rayleigh backscatter from each drop. And when your radar beam occupies n number of drops, then you get backscatter signal from all the drops, and you integrate. The received signal is an incoherent summation of the scatter signals from each drop. So that is the backscatter signal from rain. So from ionosphere, there is an ionospheric irregularities. There will be scattering. That is called a highly anisotropic. So the ionospheric irregularities are actually extended along the magnetic field, and you get the backscatter from those magnetic field. So this is actually the refractive index. Since we are talking about the refractive index fluctuations, so we will write the what's the refractive index, that is related to square root of the permittivity. The dielectric permittivity is related to the refractive index. And we take out, actually it is, the fluctuation is so small, refractive index fluctuation. It is so small, you know, a few hundred parts in a million kind of a things. That's 300 into 10 to the minus, 350 into 10 to the minus 6 deviation from unity. So you actually subtract 1, which is the air refractive index is approximately 1. So if you separate out that, you will get the fluctuating part. That is the refractivity. It's called n-1 is called the refractivity. So the fluctuation is, and that is related to the your partial water vapor pressure, partial pressure of water vapor E, and the temperature and the pressure. And the last is electron number density, and this is the critical electron number density, that is corresponding to the critical frequency that I mentioned to you before. So this is where the electrons are present. This doesn't exist in the lower atmosphere. In the troposphere and stratosphere, this part is 0. So the first two contribute to the turbulent fluctuations and the Fresnel reflection from the atmosphere. So this is the fluctuations in these quantities give the fluctuation in refractivity, and that is responsible for the backscatter from the atmosphere. And fluctuations in the electron density fluctuations, which are coupled to the neutral turbulence. So the turbulent fluctuations in 3 is provide the coherent backscatter from mesosphere. So this is actually a pictorial representation for the backscatter and Fresnel reflection. So this is actually random fluctuations of the refractive index, which is a sketch that is shown with height. And within that, there is a layered structure is there. these horizontal bars, those are the sharp gradients, and they coexist. There is a turbulent fluctuations, and there will be layers also. So if there are layers, you will get the Fresnel reflection and the turbulent fluctuation also. So you will have to separate out those two from the and the layer part reflects like a partial reflection, and this will be scattering in all directions. These are the turbulent fluctuations which will be isotropically scattering out, because these fluctuations are isotropic, refractive index fluctuations. And what does it mean by backscatter? So you take actually the fluctuations of the refractive index, and if you Fourier analyze, there is a component which corresponds to which will be coherently backscatter the radio signal. If the radio signal has a wavelength lambda, and if you have actually a component lambda over 2 in the wave number spectrum of these fluctuations, that is the spatial spectrum of this fluctuation, and that lambda over 2 component of these fluctuations, which will be sending the signal coherently back, because lambda over 2, because the signal has to travel lambda over 2 up and lambda over 2 down. So from successive portions of that component, sinusoidal component, you will get the signals adding coherently at the receiver. That's why that is what happens in X-ray crystallography. The backscattering takes place from successive planes which are removed by lambda over 2. Similar thing happens. This is a more complicated because these are not a planar kind of a thing. You will have to Fourier analyze this to find out the component, that if the component doesn't exist in that turbulence, then you do not get a coherent backscatter, and you will not be able to detect the signal. So that is actually, so this is actually a mathematical part of it, to say what I was talking about, that vertical wave number spectrum. This is the power spectrum of the turbulent fluctuations in the direction L1, L2 is the L1, M1 and N1 is the wave vector in the incident direction and is a scatter direction. And this represents a vector perpendicular to that. So this is the biscatter geometry. But if you are interested in monostatic radar, then the scattering cross section is proportional to this one, 2kx, ky, kz. That is the wave number spectrum, the component, or the lambda over 2 component when you are looking vertically up. The power in that Fourier component of the wave number spectrum. So this is a power spectral component corresponding to lambda over 2, where lambda is the wavelength of your radar. So that is the radar cross section. So it is the fluctuations in refractive index, which is actually dielectric constant permittivity, multiplied by that, weighted by that power component, gives rise to the scattering cross section. This is an involved derivation, so I would not go deep into that thing. And finally, what it tells is the scattering cross section of the turbulent backscatter is proportional to the your radar frequency to the power minus 11 over, and this is for the mesosphere, I'm sorry. For the stratosphere, this. For the stratosphere, it is f to the power 1/3. I mean, troposphere and stratosphere. This is what it is, where it is the neutral fluctuations which contributes to the fluctuations in refractive index. The next one is the third term that you have seen in the refractivity that contributes to the backscatter from mesosphere, where the electrons are ionosphere starts, electron density fluctuations are there. So the scattering is from electron density fluctuations coupled to the neutral turbulence. So the turbulence in electron density, which is electron density fluctuations, which give rise to the backscatter signals, it is strongly dependent on the frequency. That is frequency to the power nearly -4. So that is why the signal is very weak from the mesosphere compared to the troposphere. That is the backscattered signal. At 50 megahertz, if you use, you will get a very weak signal, but you can still detect if it is a very high power radar. But if you use a frequency like 2 megahertz or like that, then you will be able to detect it even with very low power radar. That is your medium frequency radar. 2 megahertz simple radar can also get the signals from the mesosphere. So these are the signals that you see. It is the okay, I skipped one. Right. This is actually what is the difference between a Fresnel reflection and a Fresnel scatter? And if there are multiple layers within your radar beam, then it is called Fresnel scatter. These layers, you will get a partial reflection from each one of these layers, and they all add up at the receiver. And if there is a single inversion layer or single stratified layer of refractive index, then you will get a partial reflection, and that is the reflection. Partial reflection is a Fresnel reflection. So the difference between Fresnel reflection and scatter is these are, summation of n number of layers incoherently to give the total signal. And here, of course, there is only one thing. So that is you talk in terms of the reflection coefficient in this case of partial reflection. So the power reflection coefficient is delta n is the fluctuation in refractive index divided by the n square, that is the refractive index square, 101 by 4. Some simplifications you make it, taking the background refractive index is close to 1. On that assumption, the deviation n1 is approximately equal to n2. On that assumption, you will get this power reflection coefficient. And for the scatter, you will have to integrate over that entire region all the reflectors. You will get actually a scatter. The delta R is the resolution height of the pulse, and the Sn dash 2k is power spectrum of the density fluctuations, gradient of the density fluctuations. If you take a power spectrum of this refractive index, vertical wave number spectrum, the gradient of the refractive index, you take the power spectrum of that, and it is proportional to that. It's a bit involved derivation, but it is similar to that turbulent backscatter thing. There it is actually power spectrum of the refractive index, and here the power spectrum of the gradient of the refractive index for Fresnel backscatter. So these are examples of turbulent backscatter. This is from the turbulent backscatter signal. And when you look at the 10 degrees east, this is the radar, Gordon-Key radar, and this is the Fresnel reflection. Fresnel reflection is a sharp spectrum, whereas this is a Gaussian kind of a spectrum. And this tells the backscatter, Rayleigh backscatter from the drop sizes. And this gives actually the drop size dependence. All the scattering cross section varies with the geometrical dimension of the with the wavelength of the radar, how it is related to the diameter of the particle. So this region is the Rayleigh region, where the radar wavelength is much larger than the diameter of the particle, and as it goes almost close to the diameter of the radar wavelength is about the same as the particle size, you get into the V scattering resonant V scatter, and eventually into the optical region. So so this is the HI, the scattering volume, scattering cross section unit volume, number of, this is the, there are a number of raindrops.
Samyukta ma'am, can you please mute? Hello.
So this is the final expression for determining the radar reflectivity of the MST radar. So this is actually a block diagram showing the MST radar, which is a 32 by 32 Aggie antenna array, and initially the radar has a limitation in the sense 32 antennas are connected with a single phase, so you can steer the beam only in the north-south and the east-west directions. And now, of course, each antenna is given as its own transmitter, so you can steer the beam in any direction you want. It's a very high-power radar. It's the radar array, 32 by 32 Aggie antenna array, across the Aggie antenna, 3-element Aggie antenna array. And these are the parameters of the radar: 53 megahertz radar, 32 by 32 Aggie antenna, and the beam width is roughly 3 degrees, located at Gordon-Key, a low latitude station. And of course, these are all various parameters. Beam can be scanned plus or minus 22 degrees. And it is the signals that are sent are what's called a coded signals. It's not simple pulses, rectangular pulses, but it is called a biphase coded signals, coded pulses, so that you can get a very high resolution. A 1 microsecond coded pulse can give a vertical profile of turbulent vertical profile of winds and turbulence, etc., or any stratified layers with a resolution of 150 meters, kind of a thing. So these are actually the maximum range resolution on the Doppler. How the Doppler range means the maximum velocity you can detect. And these are actually the various steps that the signal goes through. The signal will be detected in the receiver, and coherently integrated means the signal, one pulse signal will be weak, so you integrate a number of pulses coherently. Because it's a low Doppler signal, you can integrate, and the pulse repetition frequency is quite high, so you can integrate the returns from n number of pulses, and then you will Fourier spectrum spectrum, and then find out the moments of the Fourier spectrum. This is all the Fourier analysis thing. And a single spectrum looks like this. And if you integrate n number of spectra, you will get a spectrum like this. So this is an incoherent integration of the n number of some 100 pulses, 50 pulses. So you cannot indefinitely integrate. So this spectrum has to be stationary. If it is non-stationary, you cannot integrate. So for a limited time, you can integrate this signal to get with much less fluctuation in the spectrum. So that is the spectrum you will analyze to get the three moments. And the three moments will give you the power, Doppler velocity, and Doppler width. So those are actually the parameters that you determine. The total power of the return signal, the Doppler velocity, that is the line of sight velocity, and then the Doppler width. Doppler width corresponds to the turbulent intensity, and the line of sight velocity corresponds to the background wave, and the total power corresponds to the strength of the turbulence. So these are actually the signals from different beams. You can see the signal going up to the 20 beyond 20 kilometers kind of thing. And this is during a convective event. It's a highly turbulent signals. So at each range you will get not a single coherent signal, but multiple signals, and that is there is some complication in analyzing that signal to get the wind. So when you steer the beam of the radar in three different directions, you will get the Doppler velocities VD1, VD2, VD3 in three different directions. And from that you can find out Vx, Vy, Vz by just simply, this is the Doppler velocity, line of sight Doppler velocity. You can write as a vector with three components, Vx, Vy, Vz, and three unknowns. If you look at three different directions, you can find out. That's how the winds are derived. This is actually an example of the journal and meridional and vertical winds. And these are the winds compared with GPS sound, the radio sound, which measures the wind by tracking the GPS tracking. So you can see how exactly. So this is from the Fresnel reflection. At the tropopause, there is a strong gradient in the temperature. So there is a strong refractivity gradient. So the signal, this is an isometric plot, gives the signal falls off very rapidly and then almost to noise level, and then picks up again close to the tropopause and then falls off the stratosphere. So about 25 kilometers or so, the turbulence is so weak, you will not get any signal at all. So this is a SNR going back. So this is the tropopause. You can actually measure the tropopause height very, very accurately. This is a 24-hour plot of power of the backscatter signal, RTI plot, height and the time, and of course the color code of the thing in intensity, 20 dB. I mean, it's in dB. So this is the tropopause, and during a convective event, it can break. The turbulence could be so intense. The convective turbulence can penetrate, causes a disruption in the tropopause, and this will cause the stratospheric tropospheric exchange of ozone and water vapor across the tropopause. And that stratospheric tropospheric exchange can be studied using the MST radar during a convective event, and that is during a convective event. So these are, you can calculate the turbulence Cn square, this refractivity structure constant, which is useful for radar propagation in the troposcatter propagation of the microwaves. And this is the dissipation of eddy dissipation rates using two methods. One is the velocity fluctuation variance method, and another is the power fluctuations method. And this is actually the raindrop size distribution, actually drop size distribution. You will hear more about this from Tian Rao talk. So I will skip some of these, and I think we are pretty close to the time. This is the mesospheric echoes, comparison of the mesospheric, and so this ionospheric echoes. You can see the ionospheric echoes from less than 100 kilometers and above 100 kilometers. This is the ionospheric backscatter from field-aligned irregularities. What's called quasi-periodic echoes. It is backscatter signal from ionosphere. You can study the structure of the plasma irregularities in the E region, and this is of course a descending layer of plasma irregularity structures in the ionosphere, lower ionosphere. And this is an interesting thing that Dr. Patra will be talking about, what is called a 150 kilometer echoes, where you do not expect a plasma to be turbulent. You do a turbulent plasma instability layer, which is in a necklace shape, which varies in a necklace fashion over the time of the day. And these are actually a freezing irregularities, which are actually dramatic irregularities extending from 200 kilometers to 1,000 kilometers. The top one is the radar, and the bottom two are from the Gordon-Key radar. And these are the theoretical simulations of the of those radar plumes. And this is Rayleigh-Taylor instability. That's what people believe responsible for those depletions, plasma depletions, which are seen by the radar as a radar plumes. And these are satellite observations of those, satellite observations giving those observations of the plumes, and also the electric field polarization of those electric field within those plumes. So this is the spectrum of the plasma irregularities, and that's the rocket observation of the electron number density fluctuations. And these are very essential for the GPS applications. Madam, I think I will stop right here. I have run too fast these things, but don't worry about that. Two more talks are following to give you a comprehensive view of clear air turbulence, radar studies of the clear air turbulence, probably by Dr. Patra, the recent developments in greater detail. And later in radar meteorology talk by Dr. Tian Rao, he's going to cover all that is you need to know about how the weather radars work for studying the rainfall and the precipitating systems, and including the clouds. So I am sorry that I had to rush through because I had gone a little too slow in the history part of it. And that is a little mismanagement of the
No, sir, it was good.
But anyway, I hope I have given you the glimpse of what the high power radars can do in the study of winds, waves, and turbulence in the lower and middle atmosphere, and the plasma irregularity structures in the ionosphere, both in the E and the F regions of the ionosphere. So there are about 62 slides, and in the beginning part, probably I should have skipped some of that or gone a little faster. So thank you very much for this opportunity. And if you could probably give some 5-10 minutes for anybody to ask any questions, to that, some of the clarifications can be given, because I rushed through the slides. So it may have been a bit difficult to absorb all those all the information that I conveyed, but they can ask some basic questions about radars, how they are used for studies of the atmosphere and ionosphere. Thank you very much.
Thank you, sir. I request the participants to kindly put their questions in the chat box. So in meanwhile, let me take this opportunity to express our gratitude to sir for accepting our request for his valuable presence in this session and for sharing his insights on radar. Thank you very much, sir, for your informative session. You introduced radar in detail to our participants, starting from the history of radar to how radar technology evolved over time. Your session was indeed very, very interesting, and your experience was reflected in every word of this lecture. Your presentation had very effective flowcharts explaining simple pulse radar and many more things. You also gave a tour of formulas and the derivations with interesting graphs in investigation of ionosphere to our participants. You also gave a light on weather radar, high power radars, and a conceptual view of atmospheric structures, India MST radar with its block diagram, and also told about the tropopause detection. Sir, your humble nature and simplistic personality has definitely inspired many of us. If anyone is having any question, kindly put in the chat box. I will recite the same to the sir. Sir, we have a question by Mr. Praveen. So he's asking, when you are referring to turbulent backscattering, is it the fluid component or general electromagnetic noise?
Actually, the way to understand this, can you hear me? Can you hear me?
Yes, sir.
Yes, sir.
Oh. If I understand the question, he was asking whether it is an electromagnetic noise or what you receive is an electromagnetic noise or the signal, how to distinguish a signal from a turbulence in the atmosphere from electromagnetic noise. Is that, am I understanding?
आईपीएल वालों ने कल अनाउंस कर दिया भाई साहब कि 18 तारीख को ऑप्शन किया जाएगा और उसमें खिलाड़ियों को करोड़पति बनाया जाएगा.
Keshav Kumar, sir, can you please mute? Thank you. Yes, sir. Continue. Yes.
Let me answer the way how you get the signal from a turbulent fluctuations. Then you will, if you still have the doubt, confusion, then you can interact with me. So when you have a fluid with no variations at all, completely homogeneous fluid, then the refractive index is constant. There is no fluctuation. The way I look at it is, you can see the atmosphere as a fluid gas with a refractive index, the background refractive index N0, which is roughly 1. So the fluctuations, the turbulent fluctuations in the quantities I have shown, the temperature, pressure, and the partial pressure of water vapor. So those fluctuations make fluctuations in the refractive index, that 1. So it will become 1.00, no, that deviation is 315 to 10 to the minus 6. So whenever there is a fluctuation in refractive index, an electromagnetic wave gets scattered from that fluctuation. An electromagnetic wave will travel without any deviation and without any scattering in a homogeneous way, in a homogeneous medium. The refractive, it gets refracted when it enters from one medium to the other medium. But once that enters into the second medium, the medium is uniform, then it continues to travel. Then for any signal, however small it is, for to get back, you need some fluctuation in that homogeneous medium. So that small inhomogeneities in the medium, which are caused by the atmospheric turbulence, which is there everywhere. So which causes the each turbulent eddy to scatter, and what you get back is the collection of all those tiny signals coming from turbulent eddies. That's one way to look at, but that's a complicated way to look at. But another way to look at is simply you take that atmospheric fluctuations, spatially distributed, you Fourier analyze that, and if you Fourier analyze that, then you will have different components. Just like when you Fourier analyze a fluctuating signal in time, you will get so many frequency components. Here, you will have a wavelength components along the line of sight. So if there is a component whose wavelength is lambda over 2, then you think from each peak of that sinusoidal fluctuating component, you will get a backscatter. That's a deviation from the background. And from each one of those peaks, which is separated by lambda over 2 going up, lambda over 2 coming back, your radar signal goes between the peaks, lambda over 2 and lambda over 2 back. So the signal that returns from first peak is, let us say, pi, and then the second peak will be pi plus 2 pi, because lambda over 2, that's lambda. So those two will be adding coherently. Similarly, the successive peaks, if they are all separated by lambda over 2s, all that will be coherently adding to your signal. So that is how the turbulent backscatter is seen. That is coherent backscatter from that turbulent component. From all other components, it will be incoherent. The phases will be random and they will not be adding. So if the coherent signal will add in voltages coherently and in power in square of that kind of a thing, n square kind of a thing. So that is how the signal will be stronger, coherent signal turbulent fluctuations. And if you are in the refractive index, you will get a partial reflection. I hope
Yes, sir. Thank you very much. Sir, the next question is, how can we extract RFI from wavelets?
How can you extract?
RFI. I think it's refractive index from wavelets.
How can you extract refractive index from?
Wavelets.
Wavelets. Oh.
Yes, this was a question by someone.
I got it. No, actually,
thank you, sir.
I got you. How can you? Because actually, it is a wavelet. If you have a single pulse kind of thing, a sudden disturbance in refractive index, if you can cause something like that, it is convenient to analyze that as a single pulse. Even if you actually single disturb pulse in atmospheric refractive index, that can be analyzed. I see like a rectangular pulse, a single rectangular pulse. If you analyze, you have so many frequency components. Kind of like that, a single disturbance pulse in refractive index in atmosphere potentially can be caused by, any event, a cyclonic event or anything like that, could enhance the backscatter kind of thing. And even the return signal, if it actually very strong signal from a turbulent region, which is like a strongly enhanced turbulent backscatter as like a pulse, then it is convenient to analyze the wavelets and not get perturbation, rather through Fourier analysis. Is that what the question was?
Sir, how RFI can be extracted from wavelet? That was the question, which I think you have told in detail.
How RF
can be extracted from wavelets?
RF can be extracted from the wavelet. Oh, the RF means radio frequency. High frequency. Is that high frequency waves? How high frequency waves can be extracted from the wavelet?
Yes, sir. So the person who was having this question, can you please put in the chat box what the question was again, the wavelet question? So till then, I would like to read a few comments by the participants. They salute to you for your presentation and tell that it was very informative and excellent. So we have a lot of very good comments and feedback for your session. So in the meanwhile, I again request the participants, if they have any question, kindly put in the chat box.
So maybe at the end of the session, if we have some.
Yes, sir.
Yeah. Just one minute. So at the end of the session, after Dr. Papa and Dr. P.N. Rao talks, if there are any questions in the chat box, I can handle those questions. I'm not sure.
Okay, sir.
The second question of the, she was talking about the wavelet. The spectrum of the radar signal itself, there are some who have analyzed the wavelet analysis. I will make some comments on that one. How wavelets will come into the analysis of the radar signal. That is what the question was. Or any other question that the participants might leave in the chat box, I could answer. So we will break and.
Yes, sir. I thank all the participants too for their presence in this session. Now we have a lunch break and we will reassemble back at 2 p.m. Chandrasekhar sir, do you want to say something?
Yeah. Nothing. We just, I thought I would thank Professor PB Rao for an excellent inaugural talk. From the chat box, it's very clear that it is very inspiring, and a lot of the participants have found the talk to be very, very useful and informative. Thank you, sir, for starting this this faculty development program with your insight, and it was a very, very interesting talk, and I thank you again for your patiently answering many of those questions and clarifications from the participants. Thank you.
Thank you, Professor Chandrasekhar. I should have uniformly distributed my time along the whole thing, but I spent quite a bit of time in the history part of it. Those are the elementary slides, which are much easier to understand. So if you have recorded this talk, probably you can give to the participants and they can look through and raise some basic questions if they have at the end of all the three sessions today. And time permitting, I will be available at the end of the three sessions.
Thank you, sir. Thank you.
Okay. Thank you, sir.
Dr. Patra and Dr. Narendra also will be there. We could, we should be able to answer, give any clarifications and answer any questions that the participants may have. At the end, they should get something out of each one of these presentations. Thank you very much for the opportunity of speaking to you all, giving this lecture to the participants.